So the next talk is called Sharing Trees and Contextual Information, Reimagining Forwarding in Attribute Grammars, and Lucas Kramer from the University of Minnesota is going to present. The floor is yours.
Yeah, so welcome everyone. I'm Lucas. I work with Eric Van Wyk on attribute grammars, and I'm going to be presenting some work we did with tree sharing, and the goal of this is to let us write fewer equations and get better performance by sharing and reusing some computations. And as you'll see with some more sophisticated extensions or applications with extensible languages, it's possible to actually suddenly end up with an exponential compiler runtime if you aren't careful, which is something you obviously want to avoid. First a little bit of background about attribute grammars. I'm going to be using a really simple toy imperative language for a working example here. So we can represent languages as context-free grammars and programs as corresponding abstract syntax trees, like this one. Wrong way. So attribute grammars then are a formalism invented by Don Knuth to define the semantics of context-free languages. But they're also actually a really useful paradigm for implementing compilers. In an attribute grammar, we attach synthesized attributes on the syntax, and you can use them to compute information up the tree for different analyses like type checking or collecting a list of error messages. And then we can also have inherited attributes that pass contextual information down the tree, like for example an environment that maps names to look up their types. So formally, we can say an attribute grammar consists of a context-free grammar, which has a set of non-terminals, terminals, and productions. There's also a set of attributes, which are synthesized and inherited attributes, which can contain terms or other data structures like an environment. There's a set of occurrences that map what attributes occur on what non-terminals. And there's finally a set of equations that define the values of attributes on productions. So productions in the grammar have a signature. So for example, this if-then-else production here has a condition expression and two statements for the then and else cases. And these signature items are all labeled so that we can use them in writing equations that define the attribute values. So here the if production, for example, copies the environment down to its children and then collects error messages up the tree. And in constructing the list of error messages, we check that the type of the condition is actually a Boolean. This check is bool function reports an error message if it's not. And we also have this var production for a variable reference. This looks up the name in the environment to compute the type of this check-in scope function, and then also reports an error message if the name isn't defined. So attribute grammars are naturally modular. One can just write down productions in one grammar and then write down additional aspect equations in a different grammar and simply just compose the grammars and you get a new specification out of that. And so we can use attribute grammars to build extensible languages. We're interested in language extensions that can introduce new syntactic constructs in the form of new productions, and also new semantic analyses, transformations, translations, etc., as new synthesized attributes. And these synthesized attributes can also depend on new sorts of contextual information provided as inherited attributes. For example, consider an extension that introduces for loops to this simple imperative host language. A for loop can be translated into an equivalent while loop. We introduce a temporary variable here to avoid evaluating the upper bound more than once. This should be chosen, whatever name v0 here, not to conflict with anything. Another extension could introduce an ASM attribute on statements to translate into some new sort of assembly code. And we're specifically interested in a model of extensibility where language extensions can be developed independently. So programmers should be able to pick and choose what features they want in their language, just like they pick and choose what libraries they want to use. And this raises a question of how attributes introduced by extension A can be computed on productions introduced by extension B. This is known as the expression problem, a term given by Phil Wadler. We can somehow we somehow need to define the ASM attribute on for loops, for example, in this situation, where the for loop extension doesn't know about the ASM attribute and vice versa. So the solution that we've come up with to this is that all new extension productions need to define a forward tree on which independently defined attributes can be computed. So this is what the abstract syntax tree for a for loop would look like. A for loop is implemented by this for loop production, and it forwards to a translation containing the loop bounds and the body as children. The actual translation is a big messy tree that I'm eliding here for clarity. The for loop production might define errors directly, checking that the loop bound expressions have the right type. This requires the for loop production to pass down the environments to its children. Other independently defined attributes, like the assembly translation, are computed by default on the translation in the forwards tree, and copied from that tree to the for loop node. This also depends on the environment for those children, which it automatically gets copied the other direction as an inherited attribute and flows down through the forwards tree to the children. So this is what the definition of the for loop production would look like in our attribute grammar language, Silver. Here we define a direct equation for errors to give better error messages for when the loop bounds have the wrong type. This also requires one to define equations for the environment, since this is a dependency of errors and type on the children that we need here. And Silver features a modular well-definedness analysis to check that all needed attribute equations are actually supplied. So here, for example, we only need to supply these E and V equations because we are accessing errors on the children, and we know that errors depends on the environment. And then we define the forward to construct the while loop and the counter variable that we saw previously. And Silver distinguishes between terms, which haven't yet been decorated with attribute values, and trees that have been decorated with attributes. So in constructing the forward, we need to convert the decorated child trees back into terms so that we can decorate them again in the forward tree. And this is done by the function new, highlighted here in purple. So now consider what happens if for loops get nested. This is the rough shape of the abstract syntax tree for this code, and I'm leaving out the loop variables and bounds for clarity. So recall the definition of for loop. When we demand errors, this is provided by the explicit errors equation in the for loop production. And this in turn will demand errors from the body in the original abstract syntax tree without using the forward. And then this depends on the equation for body.environment that was applied in the for loop production. Now consider when we have the independent ASM attribute demanded by an independent extension which doesn't supply an equation for loop. Instead, the assembly translation gets automatically demanded and copied from the forward tree. And this causes the environment to be demanded in the forward tree, and it's automatically copied down from the production that forwarded to it, as you see. And note that we're actually computing the same environment in both places. This is an extra burden on the writer of for loop to have to supply the right environment that corresponds to the one that will be constructed in the forward tree, and they need to supply the correct environment in order to actually get correct error messages. And so we want to share these trees to avoid recomputing the environment. And also, we'd like to define the body's environment through forwarding, just like how synthesized attributes, like the assembly translation, were defined through forwarding. Also note here that there's potentially 4 different versions of the inner body. In this case, we don't ever actually demand the creation of the 2 middle trees, but we will see an example of that next. So now consider a negation operator that's overloaded for both Boolean not or integer negation. This neg production forwards, it dispatches to different productions based on the type of the operand. Here, error_expr is just an expression that always reports a certain error message, which is kind of useful if there's nothing valid to forward to. This specification seems innocent enough, but actually we'll see it's quite bad. Because an expression with 3 nested negations gives rise to this structure of potential forward trees. And now considering what happens during type checking, when type gets demanded from this expression, we don't supply an equation for type on neg, so type gets automatically copied from the forwards tree, And it's almost as if we wrote this explicit equation to copy the type from the forwards tree, but this is happening implicitly. And demanding type from forward tree also demands that we construct the forwards tree itself. And to decide what production to forward to, we need to know the type of the operand. And this happens recursively through every version of the tree until we reach the variable x. That should be x instead of 7 there in the expression that was parsed to give this tree. And this has to be looked up from the environment. And this in turn causes the environment to be demanded through every single term in the tree. Since environment is a dependency of type, and the operand's type is used to determine the forward, the well-definedness analysis requires that we provide that equation on the neg production. So yeah, we end up computing E and V and type on every possible intermediate forward node. And since the number of potential forward nodes is exponential in the depth of the tree, this leads to a worst case exponential amount of computation being performed. And this has actually bitten us a few times in practice. For example, we have a language extension to C that adds some Prolog style logic programming features, which is quite cool. And this works great for small examples, but there's some lurking exponential performance issues that mean it's basically unusable for any real projects we've tried. So a solution to this and these issues is to ensure that there's only ever one version of any child tree that gets decorated, and that we share this child tree between a production and in what it forwards to. So this means that any synthesized attributes demanded by the forwarding for loop production, as well as any demanded by the forwards tree, are computed on the same shared child. And inherited attributes like the environment can now also get passed down through the forward tree. And this sharing can be achieved in their Silver specifications using a new tree sharing operator, which is indicated by the @ sign. For example, @ sign body in the forwards tree here can be used, it indicates that the body should be used when decorating the forwards tree. Since we statically know that the productions in the forward will all actually supply the environment down the tree, we can actually leave out the environment equations when we're accessing errors in for loop. And we can also apply this approach to the operator overloading example and avoid the exponential blow-up problem. However, we still need to supply an equation for the environment to avoid a cycle. And that's because to compute to the type of n in order to determine how to forward, there'd be a cycle if we relied on whatever production we chose to forward to actually supply the environment to the operand. And also note that both neg and int neg are supplying the environment to the child. This isn't optimal because it requires the writer of neg to give the right equation that matches the one in int neg and bool neg, which in this case is trivial because it just copies the environment, but in practice the required equations can be significantly more complicated for some kinds of analyses. And if neg were an extension production, we wouldn't want the extension writer to have to deeply understand what's going on in all the host language inherited attribute equations. So oftentimes a hybrid approach can actually avoid needing to write down inherited attribute equations. Instead of directly forwarding to the specialized implementation, we could forward to a let expression that binds the child as a temporary variable and then refer to this variable in the specialized implementation. So this way the operand always ends up under a let expression, and that can supply the environment. And this means that the operand is now being shared under the same tree all the time. Yeah, so we can pass the environment down through the let expression, through the forwarding, instead of writing the equation in neg. And so the neg production can then always access its type on n, the operand here. So when type or any other synthesized attribute is accessed on neg, we demand it on the let expression and what it forwards to. That disappeared. Yeah, and in turn, this flows up through the specialized implementation in the body of the let expression. And more sophisticated language extensions can make this harder because they can actually introduce their own non-terminals. For example, consider a language extension that is useful for expressing complicated Boolean logic expressions. In a condition table, this expression here, consists of a series of Boolean expressions, each with an associated set of truth flags. The table expression is true only if the true or false or don't care truth flags, which is indicated by the star there, in at least one column match the truth values of each row expression. So for example, if the first two rows were false, I less than j and x equal y were both false, and the third row is true, not b, the table expression would then be true because these truth values match the second column of truth flags. And a condition table then forwards into a sequence of let expressions that bind each of these row expressions. And then this is followed by a Boolean expression, which happens to be in a disjunctive normal form that implements the truth flags. And actually note that this expression on the bottom right, this effectively mirrors the transpose of the truth flags in this column structure here. So this is what the abstract syntax tree for a condition table expression would look like. So we have a chain of cons row productions, which each have truth flags and a condition expression. And note the children are drawn in the wrong order here, from where they actually appear left to right lexically. This will help make things clearer in a second. So this is the structure of the let expression chain that makes up the forwards tree. And we'd like to share the row expression between both versions of the trees. So host language inherited attributes, like the environment, can then flow down over the forwards tree, and we can avoid the extension syntax needing to supply a host language inherited attributes to the embedded host non-terminals, the expressions in this table expression. And the extension syntax can still make use of those inherited attributes that are supplied through forwarding. For example, we can define errors on the table rows to better provide error messages for a condition table, checking, for example, that there's always the same number of truth flags in each row, and also that the row expressions actually have the right type. And this demands that the errors and type from the row expressions, which depend on the environment that was supplied through the forwards tree, actually are there. And also any independently defined synthesized attributes, like ASM to define the assembly translation, we can just simply compute that on the forward tree like normal. And the challenge now is how do we actually construct a forwards tree with this pattern of sharing? Since the row expressions aren't direct children of the condition table production that's forwarding to this translation, we somehow need a way to share trees that were decorated in one production and use them in the forward of another production. So these are the signatures of the productions that represent a condition table. The sequence of rows that make up the body of the table are represented by this T rows non-terminal. And the condition table production constructs the Boolean expression that should go at the end of the chain of let expressions. And this gets passed down the table rows using this higher order inherited attribute called cond. And this expression that we construct only refers to variable names and doesn't contain any trees that should actually be shared. And then the forward of cond table is computed using the trans attribute. This term does contain some shared trees. So if trans were an ordinary higher order attribute, this would force us to undecorate the expression and then redecorate it when the forwards tree is decorated. Instead, trans is a new sort of attribute we call a translation attribute. This is a variant of synthesized higher order attributes for the specific purpose of constructing shared forward trees. The equations that are specified for a translation attribute construct terms, just like an ordinary higher order attribute, as we can see in the nil row production. However, unlike higher order attributes, we permit sharing in a translation attribute equation, which we can see here in the cons row. And also the value of a translation attribute is a decorated tree, and we can share it just like we would share a child, as we see in the cons row and also in the con table production where we forward to the shared value of the shared tree constructed by rows.trans. So while some extension inherited attributes are explicitly defined on the extension syntax, by default, other attributes like the environment flow down through the tree that we built with the translation attribute. Thus, the environment and others don't need to be supplied on trees with the translation attribute. There's also some cases where sharing isn't feasible or isn't the right choice. For example, consider the ableC halide extension. And this is another language extension to C that we developed, which is inspired by the halide framework for image processing. Here, the programmer can write some nested for loops, along with a schedule of transformations that should be applied to the loops. For example, here, we split the outer loop into 2 nested loops with these 2 loop variables, and then unroll one of the resulting loops to generate this code on the right. And the specified loops on the left, we need to decorate this syntax with some attributes, like the environment, to compute this translation. And also note the same loop body appears in the translation, but it isn't possible to share the tree here because this requires duplicating the body. And doing that would be problematic because it isn't clear which location in the shared tree should actually be supplying the environment. And there's also some additional issues I won't get into that prevent us from using translation attributes here. However, it's not actually a problem in this case that we can't share the trees, because like the for loop extension we saw at the beginning, this doesn't really suffer from the exponential blowup issue that we saw with the overloading example. However, even so, constructs like this aren't typically nested. And the main point here is the extension developer has the choice of whether to share trees or to not share them as appropriate, and using the @ sharing operator or the new function lets the extension developer make that choice. So for evaluating this, we considered 10 existing language extensions to C. And previously we had a really brittle hack for trying to avoid some of these blow-up issues, but this was incompatible with extension inherited attributes on host language and on terminals, so it limited extensibility and had a number of other issues. So out of 74 places in these extensions where we used this hack, 39 of them could be replaced by tree sharing, avoiding writing inherited equations like with for loop. 5 of them could be shared, but involved dispatching, like with neg, where we still needed to supply inherited attributes explicitly. 15 of them we could do tree sharing using translation attributes and avoid supplying inherited equations, like with Contextual, for a total of 59. And there were 15 that shouldn't have really been using sharing in the first place, extensions like the halide extension here. The main point is all potential performance issues due to redecoration were addressed due to sharing, or addressed using sharing. And also note, in one typical example extension here, we saved 36 out of 900 lines of specification of inherited attribute equations. We didn't actually finish updating all the existing extensions yet, but this is a fairly typical example. So some modest simplifications too. We do have some future work remaining. Previously in Silver, one could just refer to the name of a child or a local to refer to the undecorated tree, and the Silver compiler would insert a call to new explicitly. This convenience feature was really kind of a mistake because this means in a lot of places where you probably intended to share the tree, it would just get implicitly decorated twice, and this would happen silently, so there's nothing to really alert the specification writer that you should maybe be using sharing here. Another thing we found is that when inherited attributes are supplied through forwarding, we often end up with circularities that are actually okay in practice because of laziness. For example, in the let binding version of neg, this works out to be okay, where we have forward depends on the operand type, which depends on the operand's environment, which depends on the forwards tree, essentially. But this actually isn't a problem. But there are some existing circularity analyses, like the one Knuth developed in his original paper and some others that have been extended for higher order attributes, which would actually flag this as a false positive, because if we tried to adapt it for tree sharing. There are some cases where we actually do have harmful cycles that are created, which we need to break the cycle by supplying an explicit inherited equation, but we'd really like a more precise analysis that would tell us when we potentially have a harmful cycle. And another area of work is in supporting, another area of work is to support dispatching to arbitrary extension reductions. For example, here we have this neg reduction that instead of forwarding to a case expression, we want to supply explicitly, or we want to dispatch based on the type to some extension reduction potentially. And that is, that leads to more flexibility, but there's currently some issues that prevent us from actually writing the specification, where the modular well-definedness analysis actually would disallow this n.env equals e.env equation. And we'd really like to also not have to write an equation for the environment and what this forwards to, because we know that it's always going to be supplied before forwarding. So in conclusion, we revisited our approach to how contextual information is handled in forwarding. We provide a more principled way to share trees and avoid recomputation of analyses. We expanded our well-definedness analysis to ensure there's no missing equations with sharing. And we demonstrated this works and is useful in ableC extensions. And overall, we're giving extension developers the power to decide when it is appropriate to share trees and giving them the tools to do so. So with that, I want to thank the reviewers for their helpful comments and feedback, and I'm open to questions if there are any.
Let's thank this speaker. Questions? Can you please walk to?
Thank you very much for your presentation. I was a little bit surprised when you brought up the translation attributes and made this comparison with higher order attributes, because I was under the impression that with the forwarding mechanism, you in some sense already generalize higher order attributes by deciding when to make copies or when to apply sharing. So could you reflect perhaps a little bit on precisely the relation between translation attributes and forwarding and higher order attributes?
Sure. So forwarding is defining the translation for a specific production, sort of the entire abstract syntax tree that it constructs. The problem that we're facing with this condition tables extension and a lot of other more sophisticated ones is if you have a whole another non-terminal or some extension language that you need to compute a translation of it and have some root production that's going to forward to that translation, you somehow need a way to build up that tree you're going to forward to and include the shared subtrees within that. Is that clarify?
Yeah, so maybe a more specific follow-up question is whether this combinatorial explosion problem that you mentioned is something that would occur if you were to use just purely functional higher order attributes.
Sorry, can you speak up a little bit? It's kind of hard to hear.
So perhaps, so if you were to use just purely functional higher order attributes, would this combinatorial explosion problem also come up?
Oh, instead of forwarding using higher order attributes? So no, so that is another alternate way of doing extensible languages, is instead of having productions individually forward, you have a higher order attribute over the entire abstract syntax tree that does a lowering pass that eliminates some productions. Yeah, that's another way of expressing it. That sort of allows different sorts of extensions. You can add, you have to make a trade-off between having some restrictions on what new productions extensions can add, or versus having some restrictions on what kinds of analyses an extension can add. And this is kind of a, forwarding, it lets you add arbitrary new attributes. And doing that kind of translation, you can't define an inherited, or you can't define an extension analysis necessarily on through forwarding in that approach. Sure.
Yeah, another question.
Yeah.
Karen.
Thank you for your talk. So I was wondering, when you put in this share annotation, do you get the exact same semantics for all the attributes? Will they have the exact same values as without the share?
So without sharing, you're creating two versions of the tree, and hopefully you got it right and supplied the right inherited attributes to the first version. But it's possible too that the extension writer could supply some environment in the extension production and then ends up getting a totally different environment in what it forwarded to. So with sharing, yeah, the goal is to only supply one version of the context.
But if you gave the same inherited attributes to all of them, the semantics would be the same, or?
Yes, if you supplied if you wrote the right equations before using sharing, then now using sharing, there should be no difference.
So could you automatically detect in that case that you could put the sharing there, or?
That's not really possible to do modular in a modular way if you don't know about all possible inherited attributes, because you can have another language extension that's adding an additional inherited attribute, and if you aren't using sharing, it might decide to supply one value before in forwarding and a different value in whatever tree you forwarded to.
Okay, but you could have a global analysis that could hint at, okay, you could put sharing here and you would get better performance, or?
You could, in theory, you could have a global analysis if you didn't care about modularity in the way we do. I think in practice, there's probably reasons that it would be something you'd want to make an explicit opt-in, I think. Yeah, you could very easily end up not sharing something that you'd expect would be shared if it was implicit, and you really want the programmer to know if they're intending something to be identical, having the identical context or not, just for helping develop extensions. Yeah.
Right, let's thank the speaker again.